Next, we completed our 2 experiments, and the first we'll talk about right now is the up and down a ramp experiment. And in this experiment, we had a ramp with a cart, and we put the origin, our position origin here, and we took our hand and just pushed on the cart, and then once it was moving, let go. So there's a region here where the cart was being pushed. And then let's say from this point onward, it's just rolling on its own. So it would have its fastest speed right here. That's when the hand lets go. Then it's slowing down till it gets to its highest point where its velocity, its instantaneous velocity would be 0. And then it's going to speed up as it's coming back down the ramp. And then we caught it and slowed it down to a stop. So this is the region here where the hand is touching it both on its way up and on its way down. Okay, so we have this motion detector that is sending out some sound waves that are bouncing off the cart and going back, and so the motion detector is sending that information to the computer, which is able to then figure out where was the cart at each moment of time. And the computer graphed the position of the cart versus time and the velocity of the cart versus time. So in your lab notebook, you should have this handout, and we're going to talk through what the graphs look like. So, and maybe actually what I would suggest you do is real lightly in pencil, sketch what you would expect those, these graphs to look like. So you already know what a position time graph looks like when something is speeding up in the positive direction. And that's what's happening here in this first segment. So this first section is when you're pushing the cart both on this graph and on this graph. So these line up, these 2 graphs like this. So these are on the same time scale. Okay, so maybe pause the video and sketch real lightly what you expect, and then I will draw what we actually found. Okay, this is what the graph looked like. When we were pushing the cart, it looked like this. Okay, and that makes sense because it started at a velocity of 0 and then it had increasing speed in the positive direction. So we have these slopes getting steeper. Now once you let go of the cart, it's now moving fast and rolling up the ramp. It's going to start to slow down. And by the time it gets to the highest point, which would be here, okay, that's in between when it's rolling up and rolling down, it should have a velocity of 0 instantaneously. So we should need a decreasing slope, and it would look like that. Then on its way down the ramp, we know that the position is going to decrease, and we know that the speed is going to increase. So it starts at a velocity of 0, and then it's going to have a greater and greater negative slope because it's speeding up in the negative direction. And now you're going to grab the cart and slow it down, so it's going really fast in the negative direction, but then it's going to slow down and end up with a 0 velocity. Now if you haven't sketched what you think the velocity time graph would be, pause the video and try that, and then I'll go over it. Okay, so here we're graphing the slope, graphing the velocity. So this would be a positive velocity, even greater positive, so faster in the positive direction, negative direction, and even faster in the negative direction. So on the way up, it is going to look like this. And then here we're going from very positive back to 0. And these are all, I'm drawing straight lines because we're doing all constant acceleration. And now it goes from 0, whoops, sorry, if you missed that. Here it was going to 0. Now we're starting with 0 and we're going to a very large negative. And then here we're going from negative to 0. Okay, and really take time to think this through and make sure that you understand why the graph looks like this, and how these two graphs relate to each other. Then we found the slope of this, and this line was actually a straight line here, so it had a constant change in velocity every second on the way up the ramp and on the way down the ramp. So the slope of the velocity time graph, so on the computer we found the slope of this, and it was around -1. So we'll just use that for the notes here. So -1 centimeter, let me just check, I think it was centimeters. Oh no, meters. -1 meters per second every second. So that means that for every second, in this second, that the velocity changed by -1 meter per second. And in this second, the velocity changed by -1. And in this second, the velocity changed by -1. And in this second, it changed by -1. And in this second, it changed by -1. Okay, so we have a constant acceleration, which is that change in velocity per unit time. And at that point now, you later can finish up by answering these research questions in your lab notebook. Our second experiment was the picket fence, which was a piece of plastic. It's about, maybe like 1 foot by 3 inches. That's the size of that. That has these stripes that are solid and transparent. And so the light can pass through when it's transparent, but the light cannot pass through when it's black. So we dropped it through a few times, and I'm just going to give you some data so that you can see how this worked. So we dropped it through several times, and here's some data from another time I did this experiment. Okay, and when we dropped it through, the computer made a position time graph and a velocity time graph. We call this Y and V. The important thing to realize with the picket fence is that because of the way we're taking data, the photo gate, all it knows, like all the information it can collect, is whether the beam is getting across or whether the beam is blocked. It is not able to collect any information about whether the picket fence is going down or whether it's going up. So when the computer uses photo gate information, it's always positive. And so the position time graph looked something like this, and the velocity time graph looked like this. So you can see we have a quadratic, we had something linear, and then what we did was we found the slope of this line, and that is how we found the acceleration. But in reality, if our coordinate system is y = 0 is the point of release, and then negative numbers are down here, really the graphs should be like this and like this. Okay, so then we see we would have a negative slope if we found the slope of this line. So these are actually negative numbers. Let's find the average, which I believe comes out to be -9.8. And at that point, you would be ready to answer the question. Let's just do that right now. According to the data collected in this experiment, what is the acceleration of an object in freefall? So the acceleration is -9.8 meters per second squared. And what does that mean? That means that in every second, the velocity of the falling object changes by -9.8 meters per second. We finished class with some notes on a very special case of constant acceleration. So the cart on the ramp, the cart up and down the ramp, it had constant acceleration, but it had a constant acceleration of -1 meter per second squared. When an object is in free fall, which we would say is when the object is moving under the influence of gravity alone, so force of gravity is the only force, that is also a situation of constant acceleration, but it's a very special case because there is a certain value that we can find, which we did in the picket fence experiment, and that acceleration, we should use A, that acceleration due to gravity is negative 9.8 meters per second squared. So we started out looking at a dropped object, and then in the homework you will do part B, which is for an object that's tossed up and then comes back down. So for a dropped object, let's first make a motion map. So at time 0, it's at rest, so we don't have an arrow. Then at time 1, it has some velocity. Then at time 2, we would draw a velocity arrow that's twice as long, because for constant acceleration, remember the velocity is changing by the same amount every second. So I'm going to draw an arrow that's twice as long. You can kind of see that's twice as long. And then at time equals 3, it's going to be 3 times. Now let's take a look at the change in velocity, because remember acceleration is change in velocity per second. So we want to know the direction of the change in velocity vector. And the way I think it's easiest to think about this is if this is to look at the velocity at one time and then look at the velocity at the next moment and ask yourself, how did it change? What did you have to add to the first velocity to get the second velocity? Whatever you had to add, that is the change. So this was 0, and then at this time it's this long. So what we have to add is something of this length. So the change in velocity vector from that time to that time looks like this. Then how did the velocity change from this time to this time? Well, we can see once again it changed by the same amount. That's what constant acceleration is. And how did the velocity change from this time to this time? It changed once again by the same amount. So the direction of the change in velocity vector is downward. So then what would be the direction of the acceleration vector? Well, acceleration is change in velocity over change in time. And we can put a little arrow over the top of these to show that acceleration and change in velocity are both vectors. They have a vector direction. Time doesn't have a direction. So when you divide this vector by the time, the acceleration has the same direction as the change in velocity. And don't worry about the length. Basically, we just want to know the direction. These all have the same length, and so these acceleration vectors compared to each other will all have the same length. That's what we mean by a constant acceleration. It's constant in magnitude and in direction. Now let's, and just to point out, the acceleration will always have the same direction as the change in velocity vector. And you notice this is pointing in the negative direction. That helps you realize why the acceleration is negative, or it corresponds to that. Okay, let's draw the free body diagram. So right when you release it, it has the force of gravity pulling down on it. What about after 1 second? It has the force of gravity pulling down on it. Force of gravity is equal to m times g, and the mass is not changing and the gravitational field strength is not changing, so this is a constant. So at every moment we have the same force. And we are looking at free fall, which is when force of gravity is the only force, so there's no air resistance. So that's why these diagrams look like this. And I'll just say one more thing about the velocities. For acceleration due to gravity, we can see that the velocity is changing by negative 9.8 meters per second every second. So if this is time 0, the velocity there is 0. After 1 second, what would the velocity be? What is this vector representing? Well, it changed by negative 9.8 meters per second during that second. So the instantaneous velocity at this moment would be negative 9.8 meters per second. Well, in the next second, it's going to change again by negative 9.8 meters per second. So the velocity at time 2 would be twice that, which would be negative 19.6 meters per second. And you can go on like that, right? Adding another negative 9.8 meters per second. Okay, we finished with an example. We have a penny is dropped from the top of the Empire State Building, which is 381 meters tall. As a first approximation, let's model the motion as free fall with air resistance approximately 0. So we're going to draw a picture of the situation, we're going to sketch the graphs, and then what we're going to do is we're going to solve for how much time did it take for that penny to reach the ground. Okay, so in your picture, what I would like to see is basically where did the object start, and then a sketch of a motion map. So I've got my little person here laying down so that they're releasing the penny at the top of the building. You should show your coordinate system. So this is y equals 0, and then where it lands is negative 381 meters. Really watch out for that negative. It has a negative displacement, and this position, according to my coordinate system, is negative 381 meters. And then sketch a real simple little motion map to show that you're thinking about what kind of motion is happening. So you always want to ask yourself, what's the motion model? Our choices so far are constant velocity or constant acceleration. So I'm going to say this is constant acceleration happening, and we're going to sketch our graphs. So, and you might want to pause the video and work ahead and then start it again to check your thinking. So it starts at y equals 0 and it ends at negative 381. So it's going to be speeding up. So it looks like this. And then this graph is going to be speeding up in the negative direction, and the slope of this is negative, and the slope of the velocity time graph is the acceleration. So this looks like this. Now we're going to use our graphs to solve and find out how much time this took. So it'd be really hard to use this graph because it'd be hard to find, the slope of this using the math that we have in our class. So let's look at this graph. This graph, we could do slope and area. So let's start with slope, and slope is rise over run. And if we look at the slope of this, we would say that the slope, we know the slope is negative 9.8 meters per second squared. It's the acceleration. We know that since the object is in free fall, that's what the acceleration is. And then we would say that the rise is the change in velocity, and the run is the change in time. And we don't know either one of those. So we have here an equation that has two unknowns. And in math, in order to solve for two unknowns, you need two equations. Well, lucky for us, we could also write an equation using area, because this is a triangle. And we know that the area of a velocity time graph is the displacement. So at the time it lands, if this right here is the time it lands, this area is negative 381 meters. But I'm getting ahead of myself. Okay, area equals 1/2 base times height for a triangle. So 1/2 times delta t is the base, and the height is delta v. So now we have another equation with two variables, but because we have two equations, we can substitute and solve. And another place you might want to pause the video and try it yourself, and then I'll continue on and you can check your work. So it doesn't matter which one you substitute into the other. I'm going to solve this one for delta v, and then substitute that in over here, and that will eliminate delta v. And then I'll have an equation that only has delta t. So I'm going to multiply both sides by delta t, which gives me negative 9.8. And at this point I'm going to drop the units. I'm not going to write the units. It gets a little messy. So negative 9.8 times delta t equals delta v. So we're going to substitute this over here for delta v. So now over here we'll have negative 381 equals 1/2 times delta t times negative 9.8 delta t. And now we're going to do algebra. So negative 381 equals, And what you want to do here, all these things are multiplied by each other, right? So the order doesn't matter. So you want to collect all the numbers in the front and multiply those together. And then we have delta t times delta t. So negative 381 equals negative 4.9 delta t squared. And put that in your calculator. Make sure you take the square root. And you will come out with... Well, that is the time for the penny to go from here to here with no air resistance. Now, really, there is air resistance, so it actually would take longer. Now what you could do is you can take this time and plug it back in over here, and you could find the velocity when it landed. And if you do that, I would suggest you do that, you'll get that delta V equals negative 86 meters per second, which is 192 miles per hour. Because of air resistance, it really doesn't get that fast, but kind of fun to solve what it would be with no air resistance.